All right. So good evening to most of you, I guess. I hope you had a great day so far. Sorry, it's a bit late in the evening for some of you. It's early morning for me, around 9 a.m. Okay, so today I'm going to be talking about solving coding problems using PEDAC. Good morning, Alexandra. Okay, so just a quick overview about me before I get started. So I'm a family man. So I have two daughters. And if you haven't seen this channel yet, hashtag Sharons. It's a nice, cute channel. We talk about our challenges and experiences while doing programming and having kids and a family. And I love programming. So I think I got introduced to programming way back when I was around early teens. My dad introduced me to it. It's something that he does regularly. So he introduced me to basic programming. If I recall correctly, those are the ones with blue screens and there's still line numbers towards the left, 10, 20, 30, 40, 50, and everything. So my first program then was a math program. It's a basic, you got a choice of addition, multiplication, subtraction, and easy, medium, hard. And it will throw at me problems that I can get to solve. And until recently, at least prior to launch school, my experience with programming has mainly been with desktop applications, particularly Excel. So with Excel, I created dashboards that you can use for productivity improvement using the VBA macro. And then I dabbled a bit in some embedded programming. I helped my dad with the program logic for a roasting machine. And then recently, and at least 2.5 years ago, I saw Tea Leaf and was thinking of shifting from desktop programs to web apps. And that's where I am right now. And prior to programming, my life was in consulting. So I was doing consulting work for process improvement, mainly doing trainings, lectures, seminars, and then, how do I say this, workshops most of the time. So that's me. And now onto the topic at hand. So what I want to do today is at least walk you through or demonstrate the PEDAC as a tool that we can use to solving coding problems. Admittedly, it's not the only one that exists. I mean, there's really lots of problem-solving techniques. If you're familiar with Six Sigma and the like, those are problem-solving techniques also. But what I want to particularly introduce to you now is PEDAC and how it can be used, or at least help us in solving coding problems. So to do this, I'll have three main parts. The first one is I want to give you guys an overview of what PEDAC is. And then the second one is at least give us some tangible reason on what's the benefit or why use it in the first place. And finally, it's the gist of this presentation. It's a demonstration of using PEDAC to solve a coding problem. And we'll be spending much of our time with this example. It's not a coding example per se. It's more about using the tool. So if you're expecting some coding, I'm sorry to disappoint, but there'll be limited coding here, but more on the process itself. All right. So in case any of you do have questions, feel free to put it, by the way, in the Q&A. I'll try to answer as much as I can after the presentation. So the first one, what is PEDAC? So there are two main things when we talk about PEDAC. There's at least two objectives for it. So one is to process the problem, and the second is we want to code with intent. So when we talk about processing the problem, there are four main steps involved here. It's basically, if you'll notice, it's majority or the entirety of the steps, and the coding is really just the last bit here. So the intention here, or at least PEDAC, is an investment in processing the problem. So process the problem, the four main steps: problem or understand the problem, examples and test cases, data structure, algorithm, and code. And when we talk about understanding the problem, what we mean here is that, at least broadly speaking, we want to get an idea of what are the inputs and outputs that we'll be needing for the problem. And if there are any requirements that aren't explicit, we'll make them explicit. So I'll talk more about what we mean by implicit and explicit later on. But the idea here is that the requirements have to be clear so that it's actionable. Or I mean, it's something that we can convert to an instruction for a computer. And then, of course, rules are there because we want to make sure that we're working within the constraints of the given problem. For instance, only use odd numbers in your coding example, those sorts of stuff. And then a mental model, which is optional. So we'll talk more about what this mental model is in the example later. And the next one is examples and test cases. Essentially, what we want to do here is validate our understanding of a problem, make sure that we are working on the right problem. Next is the data structure. It's typically the intermediary between the intermediary data that we use to convert the input to the output. It's what we work around, what we work with as we solve the problem. And last but not the least are the steps for converting input to output. And this is the algorithm. And then for code with intent, it's not to say it's not important, but when we do all of these 4 steps prior to coding, we basically already get to have a solution. So if you'll notice, the core of this thing, the process, the problem, there are just two things that we really need to take note of: the input and the output. And the PEDA, the problem, examples and test cases, the data, and the algorithm, is this black box, or this blue box already. And it's ending with an algorithm. So the objective here, at least one of the main criteria that you're done with processing the problem, is that you get to come up with a series of instructions or steps that we can give to the computer so that whatever input we have, we can convert it to the desired output that we want. And essentially that algorithm, if we think about it harder, it's really already the solution, because it gives us that, how do I describe this? The actions or the steps already that we need to do to convert the input to the output. The coding is merely the implementation of whatever solution or outline we wanted. And it can come in many forms of implementation. If you're a Rubyist, it's a Ruby program. If you're familiar with JavaScript, you can have it in JavaScript. But the thing to take note of here is that if you have that algorithm, you can basically port it to whatever programming language you're familiar with, you're comfortable with, and come up with an implementation or with the code of that solution, so to speak. So the next question is, why do we want to use PEDAC? It's a counterintuitive reason, but really it's to save time. Now, if you think about it, we're adding more steps. But those steps aren't meant to prolong it, but they are meant to avoid you going about this programming in a roundabout way, meaning you're going one direction and then, oops, it's not working well. Let me go back again, one step back. Oops, it's not working again. Let me try this direction. If you'll notice, it might seem those are small things, but those can accumulate, especially if the problem you encounter isn't something you can remedy, and you'll end up actually starting all over from the top. And that's why we want to use PEDAC, so that we can code with intent. So it looks straight now, but the intention is that it's a smoother flow. Wherein, if ever there's a refactoring that needs to be done, it's with purpose or it's with intention. It wasn't so happen that, oops, I made a mistake and something. It's really more that you're guided in how you want to go about solving it, so that when you do get to the coding part, as much as possible, it's a smooth process. Your algorithm just maps to your code. And it will essentially save you time if we do it that way. So some of the things we want to avoid, at least those are the time-consuming things that we do, I group it into 2 main groups of pitfalls. So this first set of pitfalls are those that we can encounter while we're working on the code or we're solving the code. It's not to say it doesn't happen when you do the PEDAC, but it's more pronounced if we don't do the processing of the problem first. The first one is there are requirements that are not met. This one is easy enough to happen because if we don't process the problem and we code directly, we go with an interpretation of what we think the problem is. It can be correct and it can be not, but there is that risk that if we don't process the problem, that there are requirements that we don't take into consideration. The second one, unforeseen edge cases. This one is a bit more evident if you don't process the problem. This is because it is not unlikely that there are, it's mean to say that we consider the requirement. It just so happens that we didn't consider a value, for instance. Let's say that you wanted to process some number and you wanted it to convert it into some other number. The basic thing there that we need to consider are what type of numbers are we processing. Are we allowed to receive negative numbers? Are the numbers integers only? Are the numbers decimals? What types of numbers are those? So you see, it's not so much that we didn't consider that the numbers is important, but we didn't think of what are the other possibilities. And it's likely that we'll encounter an edge case, and that edge case might throw a wrench into our implementation, and then as such prolong again the problem solving process. Finally, it can lead to hard to understand code. So as you're coding, this happens when you're coding along already and you realize I need to go back to the first step I made because it's not as effective as I thought it would be. And it'll turn out to be kind of a hack and slash approach. And you'll notice that if you do the hack and slash and you're trying to review what you previously wrote, it's not as easy to understand as compared to when you have a structure and an outline that you're following. You'll know to get back to, oh, I need to revisit step 2 first so that I can fix the other problems. And then the next one, these are more of sort of after the fact. These things happen if we want to sort of expand on a code or revisit it later on. One problem with not having at least a design is that the code becomes difficult to maintain. It's similar in spirit to the hard to understand code, but the core difference here is that since it's a completed code already and you didn't plan it out properly, the tendency is that there are unintended dependencies, especially if your solution involves, let's say, breaking down to multiple parts. Let's say you have part 1, you're handling the problem A, part 2, you're handling problem B. If you don't plan it out properly, it means that your solution for those two are dependent of each other, and that if we wanted to fix one, we have to fix the other. And typically that leads to making it an overall longer experience. And the last of the pitfalls that I wanted to at least share is that it's difficult to scale if it's not something you planned for. So it's similar in spirit to maintaining code as well, because if you want to expand on something, typically it may involve other parts. And if those parts are sort of like glued in the hip together, then it means if I want to expand on something, all others have to move along with it. And that means it's a bigger task altogether. So typically you can avoid this if we planned it out at the onset. So you'll think that, okay, if in the future I'm gonna scale this software up. So I might as well consider that whatever solution I'm gonna make is robust enough to accept different types of arguments. So that's something you can consider. I do caution about doing this prematurely though. So if there's no plan, I mean, if you're working with a team and there's no plan for that in the future, there's no need to include that. I'm just saying here that if there is a plan, it would be worthwhile to include that already when you're designing your algorithm. But if there are no plans for this in the future, there's no need to prematurely include that optimization. It will only lead to more complex code, okay? All right, so sorry, on a side note, it feels a bit different to do it at, how do I say this? I've been doing trainings before, but typically I can see the faces of the people that I'm talking to. So I know if they're able to follow along, I'm going too fast, I'm going too slow. So guys, just, if you think I'm going too fast, just, prompt or anything. So it's hard to gauge right now if your guys are there or anything. So please bear with me. So there's a tendency for me to speak a little bit fast. So just prompt, say, you're fast. Yay. Thank you. Woohoo. All right. So the next part and the gist of this is that we're going to go to the example of applying this tool. So I've chosen this for most of you. I mean, some of you, I think, have done this. I know your names, and I'm sure you've done this. It's in the challenge exercise. It's the sum of multiples problem. So just to read it through and to recap for everyone, it's the objective of this program is write a program that, given a number, can find the sum of all the multiples of a particular numbers up to but not including that number. And if it lists all the natural numbers up to but not including 20 that are multiples of either 3 or 5, we get 3, 5, 6, 9, 10, 12, 15, and 18. The sum of these multiples is 78. And finally, write a program that can find the sum of the multiples of a given set of numbers. If no set of numbers is given, default to 3 and 5. So this is the problem that we'll be working with. And for all intents and purposes, we'll treat this as the first paragraph, the second paragraph, and the third paragraph. And I'll be referring to them as such later on. So just to start it off, understand the problem. What is written? Any ideas? You can write, I mean, since I can't hear you. What do you think is written in the slide? There you go, jumping to conclusions. And technically, you guys won't be wrong but let me just reveal. It's actually not, no, it's not jumping to conclusions, but our brain is hardwired to interpret patterns. And technically, the pattern isn't wrong because we're basing it from previous experience. And it's the same thing that I want to convey with understanding the problem. So typically, when you read something, it can make sense to you already right there and then, and you'll proceed to doing something right away. But you see, we have past experiences, and those past experiences influences what we're interpreting. So if we don't dig in and spend time to digest the problem, we can do precisely that and jump to conclusions and interpret it one way when it really means another thing. I mean, it doesn't mean anything right now, but that's the intention there, that if you read it carefully and you look only at half the problem, if you look at only half the problem, it can mean something else entirely. So the key here is digest the problem, don't rush. Read carefully. I mean, it's easy. It's really easy to miss a couple of words or key phrases if you don't read carefully, because our brain fills in the gaps. You know, if you're familiar with speed reading, that's some of the things it takes advantage of. You're like interpreting the gist of the story with only a few of the words. So our brain is very good at that. It's one of the most powerful processors, pattern recognition machine. So it can crunch patterns and put in the patterns where it doesn't exist. So again, read the problem carefully. So going back, so the understanding the problem, that's our main goal here, to interpret the problem. So we'll start with the first paragraph. So I underlined a few key things here. So write a program that given a number, can find the sum of all multiples of particular numbers up to, but not including that number. So if we look at it and break it down, oops. So inputs is the target is a number. So there's the target number, and then the other input is of particular number. So numbers to get multiples from. So from here, we can deduce that there are two inputs, a target number and the numbers that we'll use to get multiples from. And then we'll notice also that there's only one output can find the sum of all the multiples. So that's the output. But that's just the first paragraph. So let's process that further. If you notice, or at least for those of you who are not into math, there's an implicit concept here. It's called multiples. And when we talk about implicit concepts, one of the things that comes to mind is the concept of problem domain. So problem domain is essentially an area for expertise or an application. For instance, in this case, it's a math domain. But one example, for instance, that a word can have, or at least have an implied meaning, is when we talk about the word balance. And look at it from 2 points of view: supply chain, logistics, and accounting. It's one word, but it has implied meaning depending on the problem domain that we're talking about. In the supply chain, when we say balance, it can particularly mean an inventory. So what's the remaining level of stock that you have? That's balance. But when you look at it from the problem domain of accounting, balance means altogether another thing. It can mean balance as in balance sheet, or balance as in credit debit, meaning the left-hand side must equal the right-hand side. But if we don't consider that, we lose some detail, and it can bite us in the end because we interpret it differently because it has an implied meaning. So another benefit of processing it, or at least considering the problem domain, is that it limits the scope of the problem, because now we're thinking of balance in a more specific way. So always consider that when you're looking at the words there. Are the words there explicit enough already for me to work with? So if it's not, you might need to do some research on it, process it further. So in this case, we get introduced to the word multiples. So multiples here what does that mean? So multiples, if we do some research and look at the math, it's actually any number that when you divide it by that number has no remainder. So if you move it from 1 to 20 and then divide it all by the first number, 3, any number that does not have a remainder when you divide it is a multiple. So 3 is divided by 3, no multiple. So 6 divided by 3, no multiple. So these are all the multiples of 3 and 5. So because all have no remainder. So that's something to take note of. And then finally, if we move to the second paragraph, so if we list all the numbers up to, but not including 20 that are multiples of either 3 or 5, you get 3, 5, 6, 9, 10, 12, 15, and 18. The sum of these multiples is 78. So since we have our input and our output, the other things we can look into are what are the rules or what are the constraints that we need to consider. And here, in this paragraph, at least we can deduce a couple. So one rule. So the multiples to be summed have to be unique. So notice that 15 is present as a multiple of 3 and 5, at least in the example on the previous slide, but it's not added twice, so it's only added once. So the multiples that we're considering are only those that are unique. So 3, 5, 6, 9, 10, 12, 15, and 18. 15 would appear twice because it's a multiple of 3 and a multiple of 5, but we included it only once. So that's something we can deduce from this one. The second, the target number input is the limit, but it is not included as a multiple. So it's up to, but not including 20. 20 would have been included as a multiple of 5 because 20 divided by 5 is 4 and there are no remainders. So, but again, it's part of the rule. So don't include the target number. And the third rule, only natural numbers are considered. Again, this one has implied meaning. So if you do a bit of research, natural numbers are actually those numbers or set of integers starting from either 0 or 1. And from a math definition, there's really two possibilities. It can start from 0 or 1. But in our case, we can assume it starts from 1 since neither of the multiples included 0. So again, this has to do with some problem domain knowledge, because typically in math, if you say 0 divided by 3, there's no remainder. So supposedly it's a multiple also. And since we don't see it here, it means to say that we are considering only the natural numbers starting from 1. Because otherwise, 0 is technically, at least from a math sense, a multiple of all numbers, because 0 divided by any number results in 0 with no remainder. So going to our last paragraph, write a program that can find the sum of the multiples of a given set of numbers. If no sets of numbers is given, default to 3 and 5. So for this one, we can also deduce another rule, and that's our fourth and final rule so far. So if no numbers to get multiples are provided, default to 3 and 5. Okay, so with that, we have some form of detail, or at least imagine it's 3 paragraphs, and we have these rules, we got some inputs. So there's really lots of things to interpret even with such a small problem. So typically, once you've got those rules, you want to review them and think if you miss out on anything. So you can check on clarificatory questions. And typically, these clarificatory questions you ask of someone or you ask of yourself or you do some additional research. So what are some of the things that we might have missed, at least going back there? So 1, what are the possible values for the target number? So we didn't explicitly say it's a target number, but the target could be a negative or some other integer. So to be explicit about it, we can say, at least we can assume that someone answered for us. It's any non-negative integer greater than 0. So it's from 1 up to some other integer number. And there will always be a value provided. So we can expect that there's no, there won't be a case that nothing is given to us. And so the next question is, how would the numbers to get multiples from target number be provided? Basically, we're checking here, what's the format of the input that will be provided for us? And if, again, we can assume someone is answering, and you can say it's an array. And third, what happens if only either 3 or 5 is provided in the array? So meaning, because it was given as a last rule that if no arguments are provided, it's 3 or 5. But this one is a bit of a tricky, sort of like, tricky question, because what if 3 was provided but not 5? What is 5 but provided but not 3? So the answer there is it wouldn't default to 3 and 5 because the rule was specific about saying if no arguments are provided or no numbers to get multiples are provided. In this case, if 3 or 5 is provided, something was provided. So we won't default to 3 or 5 and we'll just use 3 and 5. So the optional thing we can add here, and once we have all this down, is sort of come up with a summary or a picture of our representation of the problem. And this step is not always necessary. And in this step, you don't need to come up with many mental models. It's just a good way to sort of summarize what we understood of the problem. So if you go by the definition, it's a mental model, it's an explanation of someone's thought process about how something works in the real world. And by definition of model, it's a representation of the entirety. So if you look at this, there are two, at least just to give an example, there are two possible mental models that we can get once you go back and review everything that we covered. And the first one is that, to sum it up, this is a two-part problem. The first part is coming up with a list of multiples of a given number. And the second is filtering the list to contain only unique numbers. And then we return the sum of the unique numbers. And that's one mental model. It's not necessarily how to solve it. So it's not yet the solution, but it is what the problem is from your perspective. Again, it's from your perspective. It's really a mental model. It belongs to an individual. So one person can look at it differently, and there are a multitude of possibilities here. And the second mental model is this: for this problem, we need to incrementally build a list of numbers coming from multiples of a number. We'll only add to the list if the number is not yet included. Then we then return the sum of the numbers of the list. So it will end up the same result, but they're looking at it from different points of view. One is considering that I need to come up with the list first and then filter it out. And the second perspective is that I need a way to incrementally build that list. So those are two mental models of how to look at the problem once you've processed it. So when you're working on it yourself, you don't necessarily have to come up with multiple mental models. And typically, you only often come up with one because it's not that easy to add that lens, that perspective to look at the same problem in multiple points of view. So, and that's essentially the end, or at least one way to close out understanding the problem. At least from my perspective, it's good to have a summary of it. And typically a mental model, or at least is one representation of that. So the next step is the examples or test cases. And as I said earlier, our intention here is to validate our understanding of a problem, or essentially make sure that we're working on the right problem. To build on the idea earlier, if you've seen this in the jumping to conclusions, if we only look at a portion of a problem, we typically only get to see not the entire picture. So, I mean, these 6 guys were looking at it only from different portions, thinking it's a fan, it's a spear, it's a snake. And if they work on it from that point of view, they wouldn't be wrong. But if they don't sort of step back and find a way to validate, am I looking at it at the correct problem, they won't be able to figure out that they're doing something wrong. I mean, if they don't validate it and check it out for themselves, they really wouldn't know, because for all intents and purposes, their understanding is correct. So typically, one way that we want to validate our problem is we want to check on what is the expected output. And typically, we'll test it out. We'll come up with test cases. What if I had 20 and then I was given 3 and 5 as a number of multiples, and I subject it to the process? What is the expected value? And you can come up with multiples of this to consider edge cases and everything. And this alone, coming up with test cases, can maybe cover 20 minutes if we really wanted to focus on here to be, to really flesh it out and everything. This can take a while. But typically, unless in terms of if you're pressed for time, you typically want to focus only on a few test cases just to go make sure that you're on the right track, that you're not working on something different, that when you interpret it later, it will produce the expected output. So I came up with some of those, a few test cases or a few scenarios. So at least scenario 1, we are given an input of 20 and then numbers to get multiples and 78. And typically, at least this column, the output, right now it's provided for, it's available here. But if you don't, where do you get to confirm that your output is correct? And if you have an interviewer or if you have a subject matter expert, he's the person or they're the person that you tap into. If I'm given these two inputs, what is the expected output? And they'll provide you that value. So you can confirm for them. And then if it's an existing process and you're just sort of making the code aspect of it, you can look at the documentation and follow the steps and check, if I'm given this input, what is the expected output if I follow some steps and everything in documentation? And then you come out with the expected output as well. So typically, there has to be some confirmatory person or process that you need to refer to, just to make sure that your interpretation of the problem is correct and that what the output you're getting is the expected value. So some other scenarios, again, 20 and then 3, the output is 63, 20 and then 5, the output is 30, and 20 and then none, since based on the rule, if nothing was provided, it defaults to 3 and 5. So 20 and none provided is basically the same as scenario 1. And then from 1, this is the least number possible, or the target number. And then when none is provided, you get 0, because essentially this is 3 and 5, and 1 has no multiple from 3 and 5. So if you observe, at least the core test cases that I came up with are mainly based from the rules. So if anything else, at the very least, you can start off with the rules and then expand from there for the other edge cases. So at least it gives you a starting point of where to come up with test cases. You can go back to the rules and confirm what is the expected output. If I follow this rule, what is the output? If I follow this rule, what is the output? So I just played around with those and came up with 5 just to test it out. The next one is data structure. So now that we have the rules, the understanding the problem, and the test cases, we want to have a data structure that we can work with to convert the input to the output. So a consideration here is the programming language that we're going to use. It's not to say that it's the main thing, but it's important, because when we consider the programming language, it sort of scopes the possible data that we can work with. For instance, can you work with hashes? Can you work with objects? Can you work with arrays? Are those things that exist? So otherwise, you won't be able, if you don't know that, it sort of limits the data structure possibilities that you can consider. Another thing to consider for data structure, if the mental model is present, you can use that as well, because your mental model sort of gives you an idea of how you want to manipulate or play around with the data. And finally, in terms of data structure will greatly influence your algorithm. That's why typically you see these two steps together, data structure and algorithm. They're typically paired, because whatever data structure you have has to do with, will influence your algorithm and vice versa. So just be cautious about that. And typically it's just a quick step, data structure. So going to our problem, at least we'll follow the first mental model that we had. So this is a two-part problem. The first part is coming up with a list of multiples given a number. The second is filtering a list to contain unique numbers, and then we return the sum of those numbers. So if you look at it, and if you notice here, I'm framing this question. I was thinking of Ruby as a programming language. So the first one is collecting. So I need to get all those multiples. The second one is I'm filtering, and the third one is I'm reducing. So if you're looking at Ruby, it immediately jumps to mind that what I want is an array. So that's the data structure that we'll be working with. And now that we have our data structure, and typically those two are paired, we'll go to our algorithm. And for the algorithm, the main objective, at least the core for this really, is to come up with a series of instructions that will take us from the input to the output. So it's really just a series of instructions. So the difference from the mental model is that the mental model, typically this is the overlap. What's the difference of mental model from algorithm? And the typical difference is that the mental model is just a summary or your perspective of the problem. And then the algorithm is the how to it. What's the step 1? How do I get from step 1 to step 2? How do I get from the input to the output? So that's the algorithm. It's a series of instructions that take us from the input to the output. And the challenge when we work on the algorithm is that, how do I know that it's enough detail? Is it enough to say this one as the algorithm? You need to collect, then you need to filter, then you need to reduce. It's typically not enough, those three, because what we want are instructions that are enough detail so that the programming of in your programming language of choice, you can implement the rules already. Okay, so it's that level of detail that it's enough detail so that you know how to implement it in the programming language of choice. but you don't have to necessarily write it yet in the construct of the programming language. So I mean to say, let's take the case of Ruby. No need to say use an each loop, or use filter to, or use a select method of the array to filter out the elements. No need to go into that detail, because as I'll show you later on, that's more than enough detail already, and it will constrain you. So just an analogy first. I mean, just an analogy to drive home the point of not going into the implementation detail. So the problem. So here we have a development team, or at least product development team, that they're working on a shampoo. And they were given this problem that the users of the shampoo kept on complaining, the shampoo keeps falling while I'm using it during taking a bath. So it's a problem, and they wanted to find a solution for it. An analogy here is, if you go straight to this coding, it's same as saying, okay, so let's design a shampoo that has a curved shape, like a Coke bottle, so that they can have a grip in the middle. So that's going directly to coding, because that's an implementation of a solution already. So the middle part, the algorithm there, at least the middle part, the algorithm there is that the solution there is design a shampoo container that is non-slip. So there are many ways to go about non-slip. You can have it a rubber in the middle, you can have it as the Coke shape, or you can make it standing up like this so that they don't need to hold it. But if you notice, it's one step prior to the actual implementation. The solution there is that I need it as non-slip or non-falling, and the implementation is there are variants of it. You can put a rubber in the middle so that even if it's wet, it won't slip in your hands. You can change the shape of the bottle so that there's a grip. And then finally, you can make it standing up so it won't fall already and just press. So if you notice, there are different ways to implement it, but we didn't directly mention it, because if we mention it outright, we're already constraining the possibilities. And it's the same with coding. If we go directly, for instance, this is for Ruby, if you go directly with loop, each, and for, you're already constraining yourself that you have to use a for, each, and the loop. And as you get to know more about those, each have its pros and cons. And if you stick with one already, it means to say that you have to work with that construct already. And then typically, if you're stuck with that construct, if you have to change that construct, you also have to change the algorithm. And it's not so much a big problem if it were a small problem. I mean, if it's just 3-4 lines of code, go ahead, directly write the syntax of choice. It won't have that significant an impact. But if it's a big problem, typically it means that there are other parts of the algorithm that can get affected. And if that happens, it means that change will trickle down, and it will again take you some time to rethink your approach to solving the problem. Because if you're stuck with using an each already, it means to say that all other parts of the algorithm are assuming that an each will be used. Yeah, that's common. And then one problem can have multiple algorithms. So this is in line with that mental model. If you'll notice, one mental model typically maps to one algorithm. So it's one problem can have more than one approach to solving it. So and just as a gotcha, no, it's not to say here, and I'm not meaning to say don't iterate the algorithm. I mean, if you're stuck already, there's no point in beating a dead horse. Go back, start over. But the idea here is that at least if we did it intentionally, that we didn't go diving into the syntax right away, we get to minimize that chance that we need to start over again and refactor lots of stuff. So when working on the algorithm, one question typically is, how do I start? I mean, I have the data structure. What do I do now? So typically, a good place to start is if you have the mental model, you can start from there. You can just pattern. How do I implement this mental model? How do I get from that idea that I came up with and come up with the steps to implement it? So that's a good starting point. Otherwise, you can start off with the data structure like we had here and think of how do I get to implement that? I mean, tell the computer or tell the programming language to collect. How will the programming language filter and how will the programming language reduce? So those are the things that I will think about in terms of the steps for the algorithm. And when we look at it, at least from the first mental model, so we'll look at it from two mental models. So the first mental model, again to recap, this is a two-part problem. The first part is coming up with the list of multiples. And then the second is filtering the list. And finally, we return the sum. So if we break it down to steps, there will be things added. So first, create an empty array called multiples that will contain the list of multiples because we do want to collect. Then check, this is rule number 4, check if there are numbers to get multiples from. If there are none, set it to 3 and 5. Finally, loop over the list of numbers to get multiples from. So this is the part where we're building it. So for every number, set the value of current number to keep track of the incremented value because we want to check if that number is a multiple or not and add it. So and then increment current number by number while the value is less than the target number. So before every increment, add current number to multiples. So there should be a space here. Add current number to multiples. So that's the way we're building up or collecting the list. So this is the collecting part. And then if you look at number 4, filter out. So this is the filtering out. Filter out the duplicate numbers for multiples. We didn't say how yet we're going to filter it out. It should be straightforward. But filtering out, it's there. And then finally, return the sum of the numbers in multiples. And this is the third sort of big step that we're doing. So if you notice, it maps directly here to the mental model. But this one is a bit more vague. It just gives us an idea of what we think the problem is. But this one here, it's a conversion of this mental model already. So just a note, it doesn't mean that given this mental model, this is the exact algorithm you should come up with. Okay, it doesn't mean that. It's just that this is my interpretation of the mental model and how I think it should be solved. So going to the second mental model, for the problem, we need to incrementally build a list. So the difference here is notice that there is no filtering out. The loop is together. There's two things that are happening for this one. You're incrementally adding and there's a check now. So this one didn't exist earlier. So at every increment, check if the number is in multiples. If not in multiples, add it. If in multiples, do nothing and proceed to the next increment. So that's the mental model of incrementally building the list and only adding to it if it doesn't exist. So again, this is not to say that this is the only algorithm possible for that mental model. So finally, once you have that algorithm, a good step is to confirm that it is working. Test it out manually. So manually meaning you write it out in paper, do some tests in your coding environment, just to make sure that it's working properly. And for this one, we'll test it out with the first mental model and taking the case of the first scenario. So it's this algorithm that we'll be using, okay? So first, create an empty array called multiples that will contain the list of multiples. So it's easy enough. I'll create that array. Second, check if there are numbers to get multiples from. If there are none, set it to 5. So it was provided. I have 3 and 5. So I retain the inputs, so since they are provided. Next, loop over the list of numbers to get multiples from. So I'll be looping over 3 and 5. So I'll be iterating over 3 and 5. Next, for every number, set the value of current number to keep track of the incremented value. So for every number, so this will happen for every iteration. So current number equals to 3, current number equals to 5. So continuing on with the steps, so I will probably have loop over the list. This is where we left off earlier, just for reference. So next is increment current number by number while the value is less than the target number. So if we are thinking about it, it's going to look like this. It's a little bit like the code already, but you're really trying to implement it manually without writing everything together. So it's basically this. I'm going to increment current number while it is less than the target. So while it is less than the target, while current number is less than the target of 20, I will increment current number by number. So current number by number. So, but before every increment, add current number to multiples. So that's the sub-step of it. So it can, with the start of multiples 3. So add 3, then multiples 3, 6, and then so forth and so on. So you'll notice that we started off with 3, 6, 9, 12, 15, 18, because we started off with 3. And then this sort of, if you're imagining it, it's like an inner loop. So 3, 6, 9, 12, 15, 18, and then this is for the number 5, 5, 10, 15, and then up with that. So now we have the list of multiples. And then the next step is to filter out the duplicates from the multiples. And there's only one actually, and it's the 15. So we remove it from here. And finally, we return the sum of the numbers in the multiple. So if you notice, there, it's 3, 6, 9, 12, 15, 18, 5, and 10, 78. So basing on this, at least, how do I say this, quick test of the algorithm, it seems to work. I mean, no need to continue expanding it. It seems to make sense. We can try to, if you're not comfortable, you can try another example, but at least from this one, I think it should work. So now it's the last part. So, and there's not much to say here actually. It's just, we're gonna implement the code already. And this is the first mental model and the code here. If you notice, it maps directly. So the multiples and then the numbers of multiples, it's just a condition that I'm only gonna add it. I'm gonna set the value if if the length is 0 or none is provided. If it's 1, I don't care what is provided, if it's 3 or 5, and then that's the value only. And then numbers for multiples. So I use an each loop. I mean, it won't be that critical here actually. You can use a loop, and for this particular example, it will turn out that it's not that critical. So current value equals number. So we'll use that to check the incremented value already so that we're not above the target. So while current value less than target. So we're incrementally building it up. And then before, if you notice the algorithm, before every increment, so before every increment, we put in the value to multiples, and then we increment. Okay, so that's that step. And finally, since it's Ruby, just filtering out the unique is pretty easy. So you just need to call on the unique method and then inject just to return the sum. So, and we start off with 0, because if we didn't start off with 0, I mean, I missed this when I was writing the example. This will return nil because there's nothing to get. So this one is just to catch this last case. When there's nothing provided, when there's something provided here, it's 3 and 5, and the number is 1, because there won't be any multiples. So that's the value. So nil. And for the other mental model, for those of you familiar in JavaScript, I implemented it in JavaScript. This is mental model 2. So if you're familiar with the ES6 syntax, this can be a lot less concise. But if not, it will really be a bit verbose as compared to Ruby. So the difference here, the first few are the same, and actually the last is the same. It's the middle part of the mental model that's different. So now we need to check first that the number isn't existing. If it isn't existing, that's the only time we add it. So there are two things happening now in the loop as compared to the earlier one, wherein we're just putting things there regardless if it exists or not. So for this one, we're only adding if it doesn't exist. And if you notice, what I use here is a for loop just to show the difference. So it's a for loop, and that's what's gonna be added. And eventually you test it out. And again, this is just to set the handle this case. And this is for JavaScript. And with that, actually, if you'll notice, the coding part, while it is what you need to submit and it's the final output, it's just a small portion of the problem solving process. So it's really investing in understanding the problem that's critical. So to sum it up, I mean, the example here was really a bit on the verbose side of things. I mean, I wanted to give airtime for all the steps, but not all steps need to be laid out as explicitly as what we did. Particularly if you're familiar with it, some of this will happen automatically for you. Like the example of jumping to conclusions. Once you have enough muscle memory, this becomes automatic, and it may seem redundant to type it out. But depending on the needs of the problem or depending on who you're talking to, you might need to force yourself to slow down and write down those steps as you're thinking them. But again, it's not to say that those are all steps need to be laid out as explicitly. It's just the data structure. No need to sometimes explicitly speak it out. It's obvious sometimes. And then not all steps will be necessarily critical. You don't need to keep on doing all the steps. I need to start with the order also. It's not important. I mean, you don't need to start with input, output, and then identify rules, and then clarify questions, and then examples. The key thing here is that those two fall under two broad categories. Processing the problem, so the PEDA is processing the problem. The key thing to note here is that you should end with an algorithm for process the problem. So no matter which way you interpret or move this around, they will complement each other really. So if you're more comfortable with coming up with test cases first, go ahead, do that. But it's not to say it's wrong. But I mean, for me personally, it logically feels better to go from input to output in something, but some are more comfortable with starting with an example. So that's okay also. But again, I just cannot emphasize this enough. The key thing here is that you process the problem and that you end up with an algorithm. Okay, you process the problem and you end up with an algorithm so that when you get to the second part, you just code with intent, meaning you know the direction that you want to go into, and you're just trying to implement your algorithm with the code with intent. So it's not to say it will be quick, because sometimes even if you have that algorithm, it won't be as easy to convert it to the syntax, but that's the intention there, that you're iterating or taking time because you're trying to figure out how to implement it, not because you don't know yet what to do. So there's a distinction there. So you're taking time because you're figuring out how to implement it versus you're taking time because you don't know what to do. So that's coding with intent. And with that, I mean, just to close it off, just to remind you guys, PEDAC is a useful thing to add to your toolbox. So it will help you really have a better understanding of the problem and making sure that you're working on the right problem. And as you go, at least for some of you, as you move forward, you'll notice that we'll dig down more on this as you go through the 210 series. But the 100 series, we emphasize this also, but it's not part of the exact steps, but it's all important. So whenever you're working on a problem, be sure to try to think of what is the problem and how to process it first before diving deep and trying to implement it right away. So thank you, everyone. So if you have some questions, do feel free to post them here. And if you can't think of one now, just message me on Slack. My handle is @Victor. So Patrick was asking, can we apply this process at a higher level when writing with a larger web application? So the short answer is yes, but there is pre-work to be done, especially if it's PEDAC that you're implementing. Because PEDAC is designed in such a way that it's working with a non-abstract problem. Meaning, for example, if the problem is you need to come up with a good design, then PEDAC is not yet the tool you're going to need. You're still going to need something that can process an abstract concept into something more tangible. PEDAC is working for those problems that you need to define a series of steps already. So if it's a larger web application, the first step there is to be able to break down that bigger problem first into smaller problems, so such that it can be used with PEDAC. This one is a bit more experience-based to think is this problem something that is tangible already to convert from input to output. But that's the idea there. So let's take the case of, let's say, you're building, I'm not sure how familiar all of you with the logistics system. So let's say it's a fleet service system and you're dispatching, you want to create a system that can monitor and manage all your fleet outside. And that's a big application. I want to track where they are and everything. If you're thinking about it from that point of view, I wouldn't say go straight with the PEDAC, because that's a big thing to look at. Design a fleet service system. Implement what, that's difficult. So to break it down, I would say break it down into modules first. What are the components of that fleet service? I will probably have a dispatching system. I will probably have a monitoring system. I will probably have a personnel tracking system just to know who are present. And then from those three systems, I can then break it down again. From the dispatching system, what are the components? I need to be able to select an individual and then assign them a job. So if I define it that way, that for me is near a PEDAC problem already. I mean, how do I get to assign and dispatch to an individual? So what's the module that I can have for that, or what method I can have for that? For me, that's a little bit detailed already enough to work with it on a PEDAC problem. But thinking about it from that big picture, design a dispatching management system, it's a bit on the abstract level for straightforward PEDAC. Next question. Seems to me that one of the trickiest steps is identifying implicit rules. That's correct. Implicit rules. So the best case for this is, is that you come up with the test cases. If you didn't get to identify the rule, one way that you can confirm that you're wrong is that when you're writing out the rule and you're testing out the output, you get a wrong value. The person will tell you, no, that is not what I meant. The other way is that you're really just familiar that this word can have other meaning. But unless it's not clear to you that, balance is a common word. So it's not, I can imagine where you're coming from there, that balance is such a common word that it's hard to sometimes imagine that it might mean something different. So typically, when you get to the validation, that's when you get to confirm that there are things that you had a wrong interpretation of. Because unless you ask that question, or unless you test that input versus what the expected output is, it's really hard to know that you overlook something. And that's why it's really important to always come up with examples and test cases. It's that confirmatory step that you didn't misinterpret something. All right, I think that's it. There's no more questions. Thank you everyone for attending. I hope you took away something here. Have a good day.